A simple pendulum consisting of a light string and mass m and length L equals 3.6 meters is released from an angle theta equals 25 degrees, as shown in figure 2.63. How fast is the pendulum moving at the bottom of the swing? So in this problem, first thing you should always do is redraw the diagram over again to make sure you understand the problem. So we have a pendulum, a simple pendulum that's going back and forth. So it's going back and forth. It's being released at an angle theta. We're told that the length, we're told that theta is equal to 25 degrees. We're told that the length is 3.6 meters. And we don't know what the mass is. So we're told that we have to find the speed at the bottom. So we're going to use the conservation of energy, which says that total potential energy and kinetic energy is conserved. So that's coming from the work energy theorem. So, but we took the work energy, right, as F dot D, and we converted it into gravitational potential energy. So we should ask ourselves, so I'm going to take my reference level to be the lowest level here. So I want to find this height h to calculate mgh. So I know that the total energy before the release time, this is before, is going to be potential energy, but it's zero speed, so it's released, so it's zero kinetic energy, plus potential energy, which is the height. The height is, we know that if it's a pendulum, it's a circular motion, circular arc, and so we know this length is L. So the distance from this length, this triangle, tells us that this length is going to be the ratio of this side to this leg to this side, which is the adjacent to the hypotenuse. So we're looking at cosine. So this length is L cosine of theta. And so this total length from here to here is L. So the height will be L minus L cosine of theta. So our potential energy is going to be mg times L minus L cosine of theta. And the energy after, well, it'll have total kinetic energy. It's at the bottom of the swing, so it'll have total kinetic energy, which will be 1/2 mv squared. And this is what we're trying to find, so I'll circle it here. I don't know if you can see this on the board. Yeah, you can see it on the board. It's got no potential energy because my reference level, my level that I'm calculating calculations on, the height is basically 0. So this is mg times 0. So this whole term is 0, like this, 0. And so we just have to say that the energy before must be equal to the energy after. So we have that 1/2. We mixed up the order. So it's mg times L minus L cosine of theta is equal to 1/2 mv squared. This is what I'm circling. That's what we need to find, v. So the m drops away. We can move the 2 over here, and then we'll get v squared is equal to 2g times L minus L cosine of theta. And we can say that v is equal to square root of 2 g, pull out the L, 1 minus cosine of theta. And we can start substituting numbers in here. So this will be the square root of 2 times 9.8 times a length of 3.6 meters times, oops, 1 minus cosine of 25 degrees. And we should be able to calculate this in one step. So let me get my calculator out. So it's parentheses 2 multiplied by 9.8 multiplied by 3.6 multiplied by parentheses 1 minus 25 cosine close parentheses shift square root, and I get two significant digits. The answer, so we're like 2.57 meters per second, but it's going to be 2.6 meters per second. Okay, so 2 times 9.8, double check. Parentheses 2 multiplied by 9.8 multiplied by 3.6 multiplied by open parentheses 1 minus 25 cosine close parentheses shift square root, and I got 2.57, which is 2.6 meters per second. Okay, it's confirmed.